Thank you very much. I'm from Germany, and like many Western nations, we have a problem with aging infrastructure. In fact, half of all federal highway bridges that we have were constructed before 1980. So if you consider a 50 to 70-year lifespan, we are now getting into a situation where a lot of bridges are going to be needing maintenance. And the way that we do it, of course, is by using regular inspections to ensure the health and safety of the bridges. And we are documenting these using textual reports and, of course, photographs. And these data sets that we have collected then so that were collected by these inspectors, of course, they span multiple decades because of these very old bridges. Which leads us to our problem. These defect instances often have a very rough location which is recorded. So they only write down the inspectors write down the bridge component level on which this defect is located. And that makes it often hard to identify in subsequent inspections on where exactly this damage is. So if you have a photo like this on the top, this is the only indicator visually where this damage is. That makes it also hard to do comprehensive evaluation. So if you want to find out more about where this damage is, maybe there's some other indicator located on the bridge. It's very difficult to get that just from the reports. The advantage is that documentation photos are mandatory in Germany, so we have lots of visual data. And we noticed that lots of inspectors started using laser scanning to capture the current state of the bridge. So our thought was we can combine these two to basically localize the old images from past inspection reports in the new laser scans. So get an inspector out there, do one laser scan, and we can localize all the old images that we have of this bridge. And that, in the end, allows us to do a full defect map of one bridge, which hopefully helps with understanding what is going wrong with the bridge. So the method that we've decided on was key point matching. Key point matching is a method of finding similarities in images by first using a key point extractor and then a key point matcher to find homography between two images. And we've tried a few of these, a few new matching algorithms that were released a few years ago, specifically XFeed for feature key point extraction and light glue for key point matching. And these prove to be very effective in identifying photos which have very difficult features. So, for example, here we have these concrete structures with wet spots, and these matchers actually manage to identify these structures really well. So this is why we developed LiLoc, which is a Python module for doing this matching of defect images automatically for whole sets of images. And the way we do it is we first extract a panoramic cube map from the laser scans that we have, and then try to find all the images from the defect reports in the laser scans. And not only that, we also try to map the photos to each other so we can have more context, because some of these images are very close up and having more context helps. Once we have any matches, we can then project that back onto the point cloud, and that gives us a 3D position in the end. And this is our final goal, that we have a digital twin where we have the location of each defect photo with all the metadata on there on a 3D model. So let's look at some results that we have. So on the left, you can see the rectified panoramic cube map photo of the LiDAR scan. And on the right, a defect documentation image that one of our student assistants took. And this is then the feature matching that we have performed. And you can see that the structure of the concrete actually forms like a form of a fingerprint that we can use to match this photo. So these new feature matchers actually work really well on concrete. And then, of course, we can just use this image, transform it back, and now we have the 3D position and the transformation matrix between the LiDAR scan and the actual defect image. Here's a little more difficult example. You can maybe see on the top that okay. Yeah, okay, you can see the mouse. You can see that this very peculiar form of concrete can be recognized by these feature matchers and then transformed. So even if we have very difficult angles on the cameras, we can still find a good match, I would say. So we tried this on a few larger data sets. So we captured 2 data sets, one on a highway bridge with an on-ramp. This were the photos that you just saw. Where we collected 8 scan poses, 65 defect images, and then just figured out what matches to what. Our scan to photo gave us 10 matches, so 10 photos were immediately recognized in the laser scan itself, and 58 matches between photo to photo. You can see this on the right here in the figure. These are the photo to photo matches. So you can see that it makes some clusters where an inspector took multiple images of the same defect for safety or to get a good angle. And you can also see we highlighted in green all the images that were able to localize to a scan. And using these as context photos, we can also, these are the blue lines here, also then over one image over, localize other images with these context images. So we also did this. So on the first bridge, we had no false positives, which was really cool. Very nice results. We tried it on the second bridge, which was a lot bigger, a 600-meter highway bridge over a river. And there we had a lot of more false positives in the matches. So we had a lot more matches in general and a lot more images, but also a lot of false positives. So out of 900 matches, 170 were false positives. And we think that this was because we had a lower scan coverage and we also had a lot more self-similarity in the bridge. And I'm also going to show some limitations which we noticed. So this is an example of a false positive that we had. These are actually scaffoldings that were used by the inspectors to get onto the bridge. And of course, these are not the same position, but still were recognized by the algorithm. Another thing that we noticed were these crack measurement cards. Actually, the inspector held it into the photo, and of course, it was recognized as something similar. So the algorithm isn't doing anything wrong here. It's just that it doesn't expect it. Okay. Coming to my conclusion, we managed to do defect localization for legacy images through laser scanning, and we could show that AI-powered key point extractors work really well for image localization for concrete bridges. And as a little extra, we also released our code on GitHub. So this is a Python module that you can use on just sets of images. You just put your images in a folder, you run the Python script, it finds all the details. And in the future, we're trying to, of course, extend this to real data sets. So we're trying to get access to our federal database for actual images. So this is an example of actual old images from 2005 and I think 2014 is that, where it actually found out that these are the same defect, even though it's very hard to tell just by the image. But the algorithm managed to find that out. And of course, we want to use this in the future to then measure the defect progression. So if we have these mappings between the images, we can then try to measure out with, for example, with some of the algorithms for spelling detection or crack detection about how a damage progresses over time. All right, that's it from me. Thank you very much for listening.